Chapter 5 of the methods text discusses both curve fitting and interpolation. The topics related to curve fitting are also covered extensively in Chapter 6 of the notes, and were covered in previous lectures. You should also review the information that's introduced on curve fitting in Chapter 5 of the methods text, because there are some excellent examples and alternative derivations of some of the linear least squares formulas, for example. In this lecture, we'll focus on the methods of interpolation that are introduced in Chapter 5 of the methods text. Interpolation methods find a function that exactly matches the data points and then uses that function to estimate values at intermediate points. Interpolated functions will also be used later in the semester when we numerically calculate derivatives and integrals of datasets. Interpolating can be approached in one of two ways. The first way is to find a polynomial or some other function that exactly matches all of the data points in a dataset. That is, the same polynomial is used for all of the data points. If we have n plus 1 data points, then we have n plus 1 constants that we will need in our function in order to match the data at each point to the model equation. This will require an nth degree polynomial. So if we have 3 data points, we need 3 coefficients, which means we need a quadratic or second order polynomial. We'll introduce two ways of finding the coefficients for polynomials, the Lagrange interpolating polynomial and the Newton divided difference polynomial. We'll also introduce a method for finding sums of sine and cosine functions, which are called Fourier approximations. The alternative method for generating interpolation formulas is to use different polynomials over different intervals. These are called spline polynomials, and we'll introduce the calculation of splines in this chapter as well. A simple example of a spline is a linear spline, where we use a different straight line between the first and second data points than we use between the second and third data points. The Lagrange interpolating polynomial is calculated by finding n plus 1 polynomials L sub I associated with each of the data points y1, y2 through y at n plus 1, and then summing those polynomials. Here, the capital Pi indicates taking a product over these terms. In this product, since I is not equal to j, there are n terms in each product. So each of the L sub I ends up being an nth order polynomial. Notice that when we take the product of these numerator terms, if there are n plus 1 terms, but we skip the term for which j is equal to I, then we will have n terms that each have an x minus xj in them. Those n terms, when multiplied together, will give us an nth order polynomial. The denominator of each of these is a constant, and it's just the difference between two values of the independent variable x. To illustrate how this works, we'll derive the simplest Lagrange polynomial. It's a polynomial that exactly matches 2 data points, and therefore it's a straight line. The Lagrange polynomial L1 is x minus x2 over x1 minus x2, and the Lagrange polynomial L2 is x minus x1 over x2 minus x1. This gives a linear equation connecting the points x1, y1 and x2, y2. Notice that when x is equal to x1, the term multiplying y1 goes to 1, x1 minus x2 over x1 minus x2. And the term multiplying y2 goes to 0, because we have x1 minus x1 in the numerator. So the polynomial exactly matches the point y1. Alternatively, at x equals x2, the first term goes to 0 because of the x2 minus x2 in the numerator, and the second term goes to 1 because we have x2 minus x1 over x2 minus x1. So the polynomial is equal to y2 at x2. Given the data points x1, y1, x2, y2, we can rearrange this formula into a slope and intercept formula for the polynomial p1. A second order Lagrange polynomial has to match 3 data points. So for the 3 data points x1, y1, x2, y2, x3, y3, we use the same formulas to formulate L1, L2, and L3. Now, each of those L1, L2, and L3 polynomials contains 2 terms. L1 will go to 0 at x equals x2 or at x equals x3, and it will go to 1 when x is equal to x1. L2 will go to 0 when x is equal to x1 or x3, and it will go to 1 when x is equal to x2, and L3 will go to 0 when x is equal to either x1 or x2, and it will go to 1 when x is equal to x3. Therefore, when we sum the products of these L's with their respective y's, when x is equal to x1, the polynomial is equal to y1. When x is equal to x2, the polynomial is equal to y2, and when x is equal to x3, the polynomial is equal to x3. Therefore, this quadratic polynomial will exactly match all three of the data points. Notice that each of the L's is a quadratic expression in x, and at x equals x1, L1 is 1, L2 and L3 are both 0. Therefore, the polynomial takes the value of y1 at x equals x1. For n plus 1 points, the polynomials that are derived from the Lagrange method are always of order n, ensuring that there are n plus 1 constants. The formulas can therefore ensure that the curve exactly fits all of the data points. The data points do not need to be evenly spaced. The pattern is simple, but the formulas get quite complicated for n greater than 2. If data points are added or subtracted to the data set, then all of the polynomial terms must be recalculated. The Newton divided difference method is another method for deriving polynomial functions that exactly match all of the data points, and the Newton divided difference polynomials are defined recursively. The Newton divided difference method will be introduced in the next video.